So in solving systems of equations and inequalities as our next unit, this allows us to do a little bit of a review of pretty much a good chunk of the things that we've done before as well, but primarily the things that we had done at the very beginning. So especially when we're talking about the factoring and the graphing of quadratics, because if you can kind of take a good look at our curriculum here, this is actually the same curriculum that we've done before, where we're solving single variable equations. But where we're going to be tying it into further is where it's actually going to be talking about these systems. Now, we had only been talking about kind of one quadratic at a time. We had only been talking about the outcome 20.8. You'll also see here that I'm actually choosing H, I, J, K, L as the indicators for this unit, whereas before we had actually done A through G. So just kind of a continuation, but I like doing it now because it's a nice kind of review, it's a lot of stuff, as well as we'll talk about the inequalities with it. Alrighty. Let's get right into it. So we are going to, actually, I just need to fix this in your notes. This is not, we're not actually even going to do any of the algebra today. We're just going to do the graphic, or the, yeah, we're just going to solve things graphically right in this section. So to solve a system of equations, that we're trying to find out where will the graphs of these equations cross each other. So graphically, this can mean a few different things. For example, a line and a cross, or sorry, a line and a line can cross in 0 ways, 1 way, or infinitely many ways. For the 0, it would mean that we'd have to have two lines that would be perfectly parallel to each other. So the situation would be if these two lines are parallel. For one way to occur, there's actually multiple ways. We can have opposing slopes. We can have things that still can be both positive slopes. They just kind of cross at one point in time. And there's also an infinite way for things to cross. And for that infinite cross, our one line, obviously it doesn't have to be a positive line, but it could be negative as well, would be the exact same as another line. So this is just kind of putting into perspective. So we can talk about line. Now we had talked about how, in general, how lines can cross last year. We talked about that when we did our graphing. Of course, we are in pre-calc 20, so therefore we also have to talk about parabolas. So a line and a parabola can cross in 0 ways, 1 way, or in 2 ways. In general, if you have a line and you have some kind of parabola, actually, sorry, that's wrong. Line, we're going to have a parabola there. That's crossing in 0 ways. Obviously, we're going to have a parabola that's going up here, and it's still crossing in 0 ways. A line and a parabola can cross in 1 way. Now, in order for that to happen, I'm just going to change it up slightly. I'm going to change it to a negative slope. We could have some kind of parabola that just comes up to a line, or a line that comes up just to a parabola, and it just barely touches. If it barely touches it, it means it does touch. So it has crossed in a way. So cross is taken in a kind of a liberal sense, where as long as it touches, and the parabola can touch. And graphically, it means that it literally just right there. Or a line of parabola can cross in 2 different ways, or in 2 ways. I'm actually going to change it up just to make it a little more obvious. If I have a horizontal line and a negative parabola, there's 2 crosses. Boom, boom. Right. Now, nice and quickly, we've talked about parabolas before, so they can cross in 0 ways, 1 way, 2 ways, or actually in an infinite amount of way. Obviously, parabolas, for them to cross in 0 amount of ways, typically you would have to have a positive parabola and a negative parabola. It's very difficult. Actually, there is another way. We could also have potentially a parabola there, and then you'd have an inscribed parabola on the inside. Typically, you would probably make it with a little bit either the same leading coefficient or possibly a higher coefficient, just so you know that they would never cross. One way, similar to a line in a parabola. Actually, this one's, yeah. There's one parabola. There's another parabola. So, boom. One null point. 2 points. Actually, we'll have a positive parabola and a negative parabola. Boom, boom. Or even a really nice and wide parabola and a very narrow parabola. Boom, boom. Now, very similarly to the lines, for an infinite amount of solutions, you have to have some kind of parabola and the exact same parabola for an infinite solution. So let's talk about how we're going to graph these. So solve the following system graphically. We have y equals x squared and y equals x plus 2. So these are two different equations, therefore they're going to produce two different graphs. This one is a parabola. This one is a line. Now our parabola, I'm just going to rewrite it very slightly just to make it a little more kind of user-friendly. The number on the inside is 0. The number on the outside is 0. Since that's our case, this first one, actually also make that look like a 0, or sorry, I know our vertex is 0, 0, and since our line or our leading coefficient here is 1, it's that over 1 of 1, over 1 of 3, over 1 of 5, and we can do our sketch of our parabola. The line x plus 2 means that it has a y-intercept of 2, because this is in mx plus b form. Our b value is 2, our y-intercept is 2, and our slope is 1 over 1. So since this is a line, we are going to go over 1, right 1, over 1, right 1, so on, so on, so on, forth. Or it's going down 1, left 1. No matter what, our line is going to look like this. Now here's the last little catch to what we're doing, is since we're trying to solve this, we're trying to find out where does this line and parabola actually cross. We're asking, and as well as the fact that we are looking at system. A system is talking about what are the x, y coordinates for this actually crossing. So just like we had done in Foundations 10, we want to find out where are they crossing. Well, this one is crossing, this first point is at -1, 1. The second crossing is at 2, 4. Those are the coordinates of where this parabola and this line cross. If we kind of plug them into both, we would actually work out. So I'm just going to do this as a quick verbal exercise. X is -1. -1 squared is 1. Oh yeah, our y is 1. X squared, so 2 squared is 4. Yep, so the parabola definitely goes through that point. Our line, we plug -1 in here. -1 plus 2 is 1. Absolutely it is. We plug 2 in. 2 plus 2 is 4. So these coordinates definitely work here. Let's go on to another example. I'm going to solve this one by graphing. Now, we're going to hold off on graphing this top one because we're going to have to do a few different things. There's a few different ways that we can do it. Kind of like using this time as a little bit of a review of a few things. So we'll leave this one just as for a second. Let's graph this. Y equals x minus 2 squared minus 1. So that means that our vertex would be opposite on the inside, same on the outside, would be the point 2, 1, or sorry, 2, negative 1. And from there, the number in front is 1, so it's over 1, up 3, up 5, and there we go. Now, in order to graph this one, I'm actually going to change this to my green one. Yes, absolutely. We could use the formula negative b over 2a, the c subtract ah squared. That will give us our vertex. Since we had used that a little bit in our last unit, I'm going to tie back to another skill that we had done at the beginning, where we were completing the square. Because I don't want you to lose those skills, I'm just kind of bringing them back. So in order to complete the square, we did some steps. And again, just like on your stuff, I absolutely give them to you. You just have to know how to use them. So in order to complete the square, the first thing we did was factor out the a value, in this case, the number 1, from our x squared and our x term. Now, factoring a 1 out isn't going to change anything, so really, we don't have to do anything further. But what we do have to do is find half of our x term, then square it. So we have to find out what is half of negative 4. So that's negative 2. And then we are going to square it. So negative 2 squared is 4. Our next step is to add and subtract this number inside our little grouping here. Now we still can't forget about that subtract 5 at the end, because we're going to leave that there. Our next bit of step is factor the first 3 terms as a perfect trinomial square. In other words, our product and sum, a product of 4 and a sum of negative 4, will produce two similar numbers. Sorry, when I say similar, I mean they're going to be the exact same number, negative 2 and negative 2, which is this number right here before the squaring. So what happens here is it looks like this. We have that x subtract 2, a would be squared. We're then going to subtract the 4 and subtract the 5. Now this would be our next step, that we would then distribute our 1, our a value, onto here, which would just leave it there, and onto this number right here, this negative 4. But obviously 1 times negative 4 isn't going to change anything. So we can quickly simplify and get it all over and done with. We just have the 1, x subtract 2 squared, subtract 9. So now we're dealing with a vertex of 2, negative 9. Over 1, up 1. Over 1, up 3. Over 1, up 5. Over 1, up 7. And when we connect all our dots, this is what it looks like. Now here is exactly the situation where I had described before. This is actually a parabola inscribed within a parabola. These ones are never going to cross. Now, I know I typically said that we'd have a wider parabola and then a skinnier one, but because our numbers in front of each of these are 1 and 1, these are going to keep on rising at the exact same rate. These two will never actually cross each other. So the way that we say that they're never going to have any solution is either we write a 0 with a line through it inside our solution set, or we legitimately just leave nothing inside our solution set. And then we're set. Alrighty, next example. Vertex 4, 1. 4, 1. Our slope, our staircase factor is 1. So over 1, up 1. Over 1, up 3. Over 1, up 5. And that is that top parabola. For this one, well, let's graph this one. Again, opposite on the inside, same on the outside. Opposite of 4, or opposite of this subtract 4 is 4, 2. So 4, 2. This 1/3 is, instead of using the staircase method of 1, 3, 5, 7, 9, we're going to literally cut each and every single one of these numbers into 1/3 of it. Now, these are really, some of these numbers work out really nice. 1/3, 1, 5/3, 7/3, 3. So that will allow us to do this graph. So starting here, over 1, up 1/3. Over 1, up. Over 1, up 1. 1, up 1. Over 1, up 5/3, which would be that 2/3 that would be left there, and then one more full. 7/3 would be 2 and 1/3. And then up 3, no, it'll actually put us just above where that grid is. You can tell that this one is a little bit wider. But at the same time, we can see that they are obviously crossing. Now, you might be able to graph this a lot nicer than I can, because I don't see exactly where this is. So what we're going to have to do is we're going to have to just do an estimation. These are crossing at approximately 2 point something, comma 2 point something. Now, I'm just going to actually make a nicer graph to actually see where it would actually be. And when I actually look at it a little bit nicer, it's actually crossing at about, no, I actually know it. I'll show you some tricks and foundations about this, but we're doing things the hard way in pre-calc because why not? It's actually 2.775, comma 2.5. So if you approximately as 2.7 or 2.8, I would be perfectly happy with that. The next one, this is actually 5.225, comma 2.5. So that is where these two graphs are crossing. That's all there is to it. All right. One last one. Again, I'm just going to rewrite this first one so we actually have it into our vertex graphing and make it nice and easy. X squared plus 1 is the same as x plus 0 squared plus 1. So our vertex on this top one is 0, 1. Over 1 of 1, over 1 of 3, over 1 of 5. And as I'm seeing this, I should definitely add in an example. You know what? I'm going to make this negative. Just because we don't have any negative parabolas in here. So let's change this. Not that it really changes a lot. It's just instead of going up, we're going to go down. Over 1, down 1, over 1, down 3, over 1, down 5. And from there, we can do a nice sketch. Sometimes negative parabolas don't get enough love. Okay, and y equals x plus 1. Well, x plus 1 means y-intercept of 1. Slope of 1 over 1. Boom, 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 boom. And down 1, left 1. I'm graphing this nice. If you're graphing, oh, I forgot the other arrow. Gotta make sure I do that. This one is also going to cross in 2 places. And those 2 places, see, this one is -1, 0, and this one is 0, 1. If I hadn't changed this to a negative parabola, it would actually only have, it would actually cross here instead, so it would have been 1, 2. So instead of this -1, 0, it would have been 1, 2 without that negative. Obviously, that is not what our question is, so we're not using that one. That will allow you to go have some fun.